In the previous part, we have seen some important aspects of charge transport in metals. In particular, we have seen the important role played by the SD scattering in transition metals. In this part, we are going to consider the spin transport in magnetic multilayers. To do so, we need to introduce novel concepts, such as the spin accumulation and the spin current. In particular, we will see how spin current leads to a spin accumulation at interfaces. This spin accumulation gives rise to magnetoresistance in magnetic multilayers. So let's go for it.
To understand the way spin-dependent electrons travel in ferromagnets, we consider the typical density of states of a transition metal ferromagnet like iron or nickel. As we have seen in a previous lecture, the density of states is split depending on the direction of the magnetic moment of the electron with respect to the overall magnetization. In this picture, the density of states of the electron possessing a magnetic moment pointing against the magnetization direction moves up in energy, while the density of states of the electron possessing a magnetic moment pointing along the magnetization direction moves down in energy. In all the present discussion, I will call the former down electrons, represented by a blue arrow, and the latter the up electrons, represented by a red arrow. Now, I'm going to confuse everybody. Remember that because an electron has a negative charge, its spin is opposite to its magnetic moment. So electrons whose spin is aligned along the magnetization possess a magnetic moment that is against the magnetization. I call them down electrons and represent them with a blue arrow. I'm repeating myself here, but I just want to make sure things are very clear. Symmetrically, electrons whose spin is against the magnetization possess a magnetic moment that is along the magnetization. I'll call them up electrons and represent them with a red arrow. So keep that in mind when addressing Spintronics devices, because this distinction is sometimes not clearly stated in the literature. In the present model, I will consider that up and down electrons have similar velocity, but that down electrons have a larger density of states at Fermi level than up electrons. If I inject a charge current in a ferromagnet, the down electrons, which possess a large density of state at Fermi level, experience high scattering. So their mean free path is small. On the contrary, the up electrons, which possess a small density of states at Fermi level, experience weak scattering. So their mean free path is large. That's the first take-home message. In ferromagnets, the momentum relaxation time is spin-dependent, and therefore the conductivity is also spin-dependent. In other words, you could represent the conduction of a ferromagnet by an equivalent circuit composed of two parallel resistors. The resistor for up electrons is much larger than the resistor for down electrons. There is another important scaling in ferromagnets. As a matter of fact, each time an electron scatters on an impurity or phonon, there's a finite probability that it flips its spin. So an up electron can become a down electron, and a down electron can become an up electron. And the length over which this spin flips happens is called the spin relaxation length. We can define a spin flip length per spin, where tau up-down is the spin relaxation time. It is often more convenient to consider the average spin relaxation length defined this way. We're going to talk about this in a bit more details in a few slides, but what you need to consider for the moment is that this spin relaxation opens a channel between up and down charge currents. I would like to derive the actual expression for the up and down conductivities, considering both the spin-dependent mean free path and the spin relaxation. So I start with Boltzmann equation that I extend to spin-dependent transport. Now I have two equations, one for up electrons and one for down electrons. And you can see here the spin-dependent momentum relaxation time and the spin relaxation time. I can use the same technique I used in the previous lecture. I multiply each equation by the velocity, and I simply integrate over the momentum space to obtain the charge current in each spin channel. I obtained these two coupled equations, where I highlighted the conductivities for up and down electrons so that you can track them. And after a few manipulations, I get the expression of the conductivity of each channel. You see that the spin relaxation enters this definition in a complex manner. Now, let's see if this makes sense. If we consider a long spin relaxation time, much longer than the momentum relaxation time, then the two channels are decoupled, and we obtain two parallel conductivities for up and down electrons. That's fine. Now, if the spin relaxation time is much shorter than the momentum relaxation time, then the up and down channels are merged together as electrons flip very quickly from one state to the other, and the conductances of up and down channels are equal. So this is reasonable. Now, how can we validate this model? To address the validity of the two-channel model, I will follow a pioneering experiment by Fert and Campbell published in 1968. Based on the model developed above, the resistivity of a ferromagnet modeled as a parallel resistance circuit should read like that, where the spin relaxation is modeled by a spin flip resistivity. You might remember from the previous lecture that each spin channel should fulfill Matheson's rule that separates the resistivity into a temperature-independent contribution due to the scattering against impurities and a temperature-dependent contribution due to scattering against phonons. I can inject Matheson's rule into the definition of the resistivity and rewrite it this way. This expression is a bit tricky, but the bottom line is that you can separate it into a contribution that does not involve spin flip and is proportional to the temperature-dependent resistivity, and a contribution proportional to the spin flip resistivity. Therefore, by studying the temperature dependence of the resistivity of a ferromagnet when varying the doping, you could get an estimate of the spin relaxation. This is what Fert and Campbell did in their paper. They considered pure nickel and nickel doped with chromium and investigated the temperature dependence of their resistivity. Here you have the resistivity of pure nickel marked by the small squares, and here the deviation of this resistivity from Matheson's rule marked by the small circles. Now, if you look closely at this second curve, you'll see small crosses. It's not easy to distinguish, sorry for that. These small crosses are the data for nickel doped with chromium. And you see that at small temperature, the data for pure nickel and the data for nickel chromium merge together on the same curve. At large temperature, though, these curves do not overlap anymore and go away from each other. What you need to keep in mind is that the top curves are deviations from Matheson's rule, so they should display no thermal dependence, at least in principle. The interpretation given by Fert and Campbell is that the low temperature behavior that is independent on the impurities is due to the spin flip relaxation against phonons, this row up-down that I introduced phenomenologically. To be frank, this is quite a complex experiment to interpret. And now, 50 years later, we can produce data that is much easier to analyze. However, this pioneering experiment is probably the first demonstration that spin relaxation is such a crucial ingredient for spin transport in magnetic materials. Where do we go from here? Well, from the data of the previous slide, one can extract some materials parameters like alpha and mu, which reflect the imbalance between up and down resistivities. The next step is to confirm that the parameters extracted from the experiments are meaningful. To check that, Fert and Campbell measured the resistivity of nickel now containing two types of impurities, like chromium and manganese. Based on Drude model, we know that the conductivity is proportional to the momentum relaxation time, which is itself spin dependent and proportional to the impurity concentration. If you put two types of impurities in a metal, then the momentum relaxation should look like that. In this expression, I consider that the scattering events against two types of impurities are completely uncorrelated, which is correct in the limit of weak doping. Then I obtain the following scattering time, and finally I get an expression for the spin-dependent conductivity. Assuming that the current is carried in parallel by the two spin channels, I get this expression for the resistivity. Notice that now I consider very small temperature so that I can neglect spin relaxation. And I obtain the following expression for the deviation from Matheson's rule. The deviation is now expressed with parameters I can extract independently. I have the resistivity when the metal only has one type of impurity, ρ A, ρ B, and the corresponding asymmetry parameter, alpha A and alpha B. Using the parameters extracted from the previous experiment, Fert and Campbell were able to reproduce the deviation from Matheson's rule of nickel doped with both chromium and manganese. This second experiment validates the overall model. This discussion leads us to two take-home messages. First, the two-channel model proposed by Mott is valid in magnetic transition metals. Second, the spin relaxation is a key ingredient of spin transport in metals. Although Mott's two-channel model came as early as 1936, it took about 50 years to implement these ideas in an actual device. The reason is because the scales that characterize the spin transport are typically the spin-dependent mean-free path and the spin relaxation length. These lengths do not exceed 10 to 100 nanometers, so you need thin film deposition and microfabrication technology to build such a device. As I mentioned at the beginning of this lecture, this was achieved in 1988 by Fert and Grunberg. Now let's use our knowledge on spin transport to understand what's happening. The typical system is represented here. I have two ferromagnets separated by a thin spacer. I'd consider the Knudsen regime, where the size of the system is comparable to the mean-free path. If the two magnetizations are parallel to each other, the up electrons are weakly scattered in both ferromagnets, whereas the down electrons are strongly scattered. Therefore, the total conductivity is dominated by the up electrons. Now, if I switched one magnetization and consider the anti-parallel alignment, up electrons are weakly scattered in the top ferromagnet, but strongly scattered in the bottom ferromagnet. The down electrons do exactly the opposite. So eventually both electron species have the same conductivity. This gives rise to the magnetoresistance. Now, I have been looking at the regime where the thickness of the layers is comparable to the mean-free path. What happens in the diffusive regime? What happens if the thickness of the layers becomes much bigger than the mean-free path? In this case, the electrons scatter strongly everywhere. The momentum scattering is so strong that the electron loses its momentum memory. In a sense, it doesn't remember where it's coming from. So it diffuses from one layer to another and doesn't make much difference between scattering across parallel and anti-parallel configurations. The electrons are incapable of transporting spin information. It's a very subtle effect that only occurs in this geometry when the current is injected in the plane. In a couple of slides, we'll see that this doesn't happen when the current is injected perpendicular to the plane of the ferromagnet. To model the magnetoresistance in the current in-plane geometry, one needs to use the Fuchs-Sondheimer theory I mentioned in the previous lecture, because this theory keeps track of the momentum of the electrons. Here I show such calculations performed by Kamli and Barnash using Fuchs-Sondheimer theory. On the ordinate you have the magnetoresistance, and on the abscissa you have the mean-free path. When the mean-free path goes to zero, the magnetoresistance vanishes. I would like to say a few words on the spin relaxation. First, when we talk about spin relaxation, we do not mean that the electron itself loses its spin. Of course, the spin is an intrinsic property, so it doesn't disappear. What disappears, though, is its orientation. The interaction between the electron spin and some fluctuating magnetic field randomizes the spin orientation, and therefore, after a while, it is not possible to attribute a given direction to the spin. This is the spin relaxation. To see how it works, I consider an isolated spin in a time-dependent fluctuating magnetic field. We know that the spin will do its best to precess around the magnetic field and eventually align with it. The time it takes for the spin to achieve a full precession is called the precession time, and the time it takes for the magnetic field to reorient itself is called the coherence time. If the coherence time is long compared to the precession time, the spin can achieve many precessions before the field reorients itself. Therefore, the spin remains mostly aligned on the magnetic field, and the spin relaxation time, the loss of spin memory, is directly proportional to the coherence time. On the opposite, if the coherence time of the magnetic field is much shorter than the precession time, the spin has a hard time to follow the field direction. It can only precess by a small angle before the magnetic field reorients itself. Therefore, the spin relaxation time is inversely proportional to the coherence time. This simple picture gives us two limiting cases, and as we'll see in a minute, most spin relaxation mechanisms fall in either category. Consider first a metal in which some magnetic impurities are randomly distributed. These impurities do not interact with each other, and therefore their magnetic moment is random. When electrons flow in such a material, they scatter against these impurities, and their spin experiences a small kick that randomizes their direction each time they scatter against such impurities. So the stronger the scattering, the faster the spin relaxation. This is the first case we have seen in the previous slide. The precession time is much faster than the scattering time. Now let's consider another important class of effects, the Elliott-Yaffe scattering. This one does not involve magnetic impurities, but only scattering against non-magnetic defects and phonons. Because there is spin-orbit coupling in the band structure, the electrons have a finite probability to flip their spin upon scattering. We are still in the first case discussed above. The faster the scattering, the faster the relaxation. Finally, I'd like to mention one last class of spin relaxation mechanisms that also involves spin-orbit coupling, but not just any kind of spin-orbit coupling. This mechanism, called Dyakonov-Pereyle, involves spin-orbit coupling in non-central symmetric materials. In these materials, like asymmetric two-dimensional electron gas, semiconductors with zinc-blende crystal structures, interfaces, and so on, the spin-orbit coupling becomes linear in momentum. This is something I've already seen in the context of interfacial magnetism. In the present example, I consider Rashba spin-orbit coupling that is linear in momentum. When you send an electron in such a material, its spin precesses coherently around the spin-orbit field due to Rashba. When you send an electron in such a material, its spin precesses coherently around the spin-orbit field due to Rashba. This precession is coherent, but because you have so many electrons with different momentum involved in the transport, all these precessing spins interfere with each other, which randomizes the overall spin direction. However, upon momentum scattering, the electron momentum changes direction, and so does the Rashba field. So from the spin perspective, the Rashba field around which it precesses changes direction after each scattering event. So the scattering actually quenches the effect of the Rashba field. This is an example of the second case we discussed in the previous slide. The stronger the scattering, the slower the spin relaxation. How do we measure spin relaxation? To answer this question, we actually need a bit more knowledge about spin transport. But for now, let me just outline a couple of techniques to give you an idea. In semiconductors, for instance, spin relaxation is usually probed by optical means. Spin polarization is excited via circularly polarized light, and its time dependence is probed by a secondary laser through magneto-optical Kerr effect, for instance. An example is given here where the signal measures the damped precession of the spin density around the external magnetic field. This signal is fitted by this formula, where the cosine accounts for the precession and the exponent accounts for the relaxation. And this way you can access the spin relaxation time. In metals it's a bit different because it is more difficult to create a spin density optically. So spin relaxation is usually measured electrically using Spintronics devices such as spin valves. Varying the distance between two ferromagnets and measuring the overall magnetoresistance provides a direct access to the spin relaxation length. One can also use static Handler effect, which measures the alignment of the spin density along an external applied field. The broadening of the signal is directly related to the spin relaxation length. I realize that I'm going very fast here, but I'd like to attract your attention on the typical range of values measured experimentally. Just keep in mind that these numbers are just meant to give you a rough idea and depend substantially on the quality of the material itself. So for N-doped gallium arsenide, Kikawa and Ashalom reported a spin lifetime of about 1 nanosecond at 100 K, and very long 100 micrometer spin diffusion length around 1.6 Kelvin. In N-doped silicon, Ron Jensen's group has reported 140 nanosecond spin lifetime at room temperature, corresponding to a spin diffusion length around 230 nanometers. These are very big numbers. Graphene is even more impressive, as the spin diffusion length can exceed 1 micrometer at room temperature. The very long spin diffusion length is associated to the weak spin-orbit coupling of these materials. As far as metals are concerned, copper shows the longest spin relaxation length, around 100 nanometers at room temperature, while cobalt and platinum, which possess larger spin-orbit coupling, have spin relaxation length around 5 to 10 times smaller. Again, these are just indicative numbers, but they give a good idea of what's going on. If you want to learn more about this research direction, I encourage you to have a look at these comprehensive reviews. We now have enough in our hands to enter the very heart of spintronics and consider spin transport. In the previous lecture, we have seen that in the drift diffusion regime, the charge transport is governed by the following equations. The first equation is the definition of the current density, that is composed of a drift term and a diffusive term. The second equation states the conservation of the charge density. To make things a little bit simpler to track, I'll introduce the chemical potential mu and rewrite the definition of the current density this way. I want to extend this equation to spin-dependent transport. There are several methods to do that, such as the Boltzmann equation or the quantum kinetic equation. But in this lecture, I'm going to adopt a very practical approach that gives about the same results as these fancy techniques. I consider the two-channel model that states that a charge current comes from the contribution of up and down electrons. So the current density Jc can be written as J up plus J down. I can also define the imbalance between up and down current. I'm going to call this imbalance the spin current. Now the spin current is really a current of angular momentum. So its unit should be h⁻²/2 per second per meter square. But it is much more convenient to express the spin current in terms of a charge current. So I'll take the difference between up and down currents, whose units is in ampere per meter square. I'll divide by the charge to obtain the particle current density, and I will multiply by h⁻² to get a spin current density. In most calculations, I will either keep h⁻²e explicitly or simply drop it and express the spin current in the same units as the charge current. But we always should keep in mind that a spin current is a current of angular momentum. Now what happens if I have an equal amount of current in the two spin channels? Well then, I have non-zero charge current density and zero spin current density. But if there's an imbalance, say I have less down electrons than up electrons, then I have a positive spin current. If I have more down electrons than up electrons, I end up with a negative spin current. You see that the sign of the spin polarized current depends on both the spin direction and the flow direction. Now I can push this reasoning forward and even build up a current made of two counter-propagating spin polarized currents of opposite spin and equal magnitude. In this case, I have zero charge current and I have a pure spin current. This pure spin current has been attracting a lot of attention and a lot of hope because it constitutes a means for transporting information without Joule heating, because there's no charge transport, but only spin transport. I can extend the same ideas to the density. Again, the charge density is the sum of up and down electron density, and the spin density is just the difference, multiplied again by h bar over 2e. Now you could also define the magnetic moment this way. It's very important here to emphasize that the charge density we're talking about is a non-equilibrium property. It only exists if there's a current flowing in the system. So the spin density and the magnetic moment associated with it are also non-equilibrium. They are sometimes called non-equilibrium magnetization. As we will see in the next slide, it's also quite useful to define a spin-independent chemical potential, which is simply the average of mu up and mu down, as well as a spin-dependent chemical potential, that is the difference between mu up and mu down.
Armed with these definitions, we can build the spin-dependent drift diffusion equations. Here are the three equations that govern charge transport in metals. I can simply extend them to up and down electron channels. Adopting the definition of the charge current density and spin current density, I obtain these two equations that I can rewrite this way. Here you see that I define the total charge conductivity sigma c and the current polarization beta. This beta parameter tells you how much the material can spin polarize a current. Of course it cannot exceed 1, but it can be 0 or even negative. Now I can do the same with the density, and I obtain the continuity equation for the charge density and the continuity equation for the spin density. No, there's an issue here. The charge is definitely a conserved quantity, but due to spin relaxation, the spin is not, at least on the semi-classical level. To take into account spin relaxation, you must add a term that absorbs the spin density. Of course, you can derive this term using quantum kinetics or Boltzmann equation, or you can also simply introduce it by hand. Now, in most cases, we will be concerned by steady state, and therefore, we will be using this equation. It connects the divergence of the spin current to the spin chemical potential and explicitly takes into account the spin diffusion length. The coefficient in front of the spin current seems a bit complicated, but don't worry. In our forthcoming calculations, we will absorb the 2e over h bar coefficient into the definition of the spin current. The drift diffusion equation has been the object of many theoretical works in the late 80s and early 90s, and it is difficult to give a full account of this vast literature. Therefore, I just mentioned to you what is considered as the standard reference in the field, the famous paper by Thierry Vallée and Albert Furt, where the spin-dependent drift diffusion equation is derived based on semi-classical Boltzmann equation. My goal is now to obtain an analytical formula that describes the way the spin density behaves at the interface between a ferromagnet and a non-magnetic metal. To do that, we have four equations, 2 for the charge and 2 for the spin. I will consider a one-dimensional model so the spatial variations only happen along x. Combining the top two equations and the bottom two equations, I obtain this second-order differential equation that couples spin-independent and spin-dependent chemical potentials.
Here, beta is the polarization of the conductivity, and lambda SF is the spin diffusion length. I can solve these equations and obtain an explicit expression for the spin-independent chemical potential mu bar and the spin-dependent chemical potential mu s. You see that mu s is the sum of two exponentials, which is really the hallmark of diffusive transport. At this stage, I set beta positive in the ferromagnet, and I call its spin diffusion length lambda f. In the non-magnetic metal, I take beta equals 0, and its spin diffusion length is lambda n. I have now a very simple problem to solve. I simply need to make sure that the spin-dependent chemical potential doesn't diverge away from the interface. And I will assume that both the chemical potential and the spin currents are continuous at the interface. In other words, I consider that there is no interfacial spin relaxation and that there's no interfacial resistance coming from disorder or band structure mismatch. As a consequence, at the interface, the spin-dependent chemical potential on the non-magnetic side equals the spin-dependent chemical potential in the ferromagnetic side. By doing so, I obtain these expressions for mu s. You see that mu s is proportional to the charge current density. So it is a non-equilibrium effect, and it depends on the direction of the current. By adopting some reasonable parameters, I end up with this graph. The red curve is for electrons going from right to left, and the blue curve is for electrons going from left to right. You see that the spin-independent chemical potential increases in the vicinity of the interface. Since it is proportional to the non-equilibrium spin density, it means that the spin density accumulates at the interface. This is called the spin accumulation, a key concept in spintronics. What is the consequence of this spin accumulation and the transport property of this interface? To see that, I can look at the way the spin-independent chemical potential mu bar changes from far away left to far away right. This is what I get. Here, I take the chemical potential in the non-magnetic metal as the reference. Of course, this chemical potential also depends on the current direction. The ratio of the difference between these chemical potentials and the current density gives you the interfacial resistance. This interfacial resistance looks like that. You see that accumulating spin density against a magnetic interface changes the resistivity of the whole system. This is something that was pointed out by Johnson, Silsby, Vincent, and co-workers, just 1 year before the observation of the giant magnetoresistance.
Let's ask ourselves this question. How does a charge current become spin polarized when I inject it from a non-magnetic metal into a ferromagnet? What controls the buildup of the spin polarization? To see that, I enhanced the previous model by adding interfacial resistance. As I mentioned in the previous lecture, this resistance is not related to spin accumulation, but rather to band structure mismatch between the non-magnetic metal and the ferromagnet. So instead of assuming that the spin accumulation is continuous at the interface, I need to apply Ohm's law. I assume this relation applies independently to up and down electrons, and I can deduce a boundary condition for the charge current and the spin current. Gi is the mean interfacial conductance, and gamma is the interfacial polarization. By using these boundary conditions, I obtain the spin current flowing inside the ferromagnet. Here I'm focusing on the ratio between the spin current and the charge current, which tells me how much the charges that flow inside the ferromagnet are polarized. This expression involves several new parameters. We have the polarization in the bulk of the ferromagnet that tells me how much I can polarize my current far away from the interface. Most interestingly, the polarization close to the interface is controlled by 3 resistances and 1 scaling length. The scaling length is easy to understand. Since we inject a current from the non-magnetic metal into the ferromagnet, I virtually start from 0 polarization.
so it takes some distance for these unpolarized spins to flip and become polarized. This distance is given by the spin diffusion length of the ferromagnet. The shorter the spin diffusion length, the faster the polarization builds up. And that's something quite easy to see. In this calculation, I turned the interfacial resistance to 0 for simplicity. The blue curve is the spin polarization profile when the spin diffusion length of the ferromagnet is very long. And you see that the spin polarization saturates only far away from the interface. Now, if I reduce the spin diffusion length, you see that I can get maximum polarization closer to the interface. Now let's consider the influence of the interfacial resistance. In the expression of the spin current, the amount of spin current flowing through the interface is given by the ratio between different resistances, given in the green box. There's the interfacial resistance that comes from the band structure mismatch between the ferromagnet and the non-magnetic metal. And we also have two new resistances that are defined as the ratio between the spin diffusion length of a given layer and its bulk conductivity. I call them spin resistances. They basically tell you how easy or hard it is for a spin polarized electron to penetrate into the metal, be it non-magnetic or ferromagnetic. The shorter the spin diffusion length, the easier it is for the spin current to penetrate the metal. So bottom line, if you want to achieve high polarization at the interface, you need large interfacial resistance, as shown in this figure. The black curve represents the case where there's no interfacial resistance, while the red and blue curves present very high resistance. The higher the interfacial resistance, the higher the interfacial spin current. Now I'm going to change perspective and explore how one can inject a spin current into a non-magnetic metal. As a matter of fact, if you want to transfer spin information from one part of a device to another, you need to be able to inject the spin current efficiently in the non-magnetic channel. So I'll use the same procedure as before and concentrate on the spin current profile inside the non-magnetic metal. That's an interesting formula. You see that the current polarization is proportional to the bulk polarization of the ferromagnet times the spin resistance, and to the interfacial polarization times the interfacial resistance. So let's look at the spin current profile across the interface when assuming no interfacial resistance. You see that the amount of spin current that you can inject into the non-magnetic metal decreases when decreasing the conductivity of the metal. The more resistive the metal, the more difficult it is to inject a spin current into it. This is an important observation because it challenges the possibility of injecting spins into semiconductors. As a matter of fact, if you want to create a spin current, the easiest way is to use a transition metal ferromagnet where the current polarization is strong. The problem is that the resistivity of this ferromagnet is quite small compared to the resistivity of semiconductors. Therefore, it seems pretty vain to try to inject spins from a metal into a semiconductor. Actually, there's a way. You can use the interfacial resistance. This figure considers the spin injection from a good metal into a bad metal with a conductivity 100 times smaller. If you have no interfacial resistance, then I just can't inject spins. This is the black curve. But if I start increasing massively the interfacial resistance, say up to 10,000 or 100,000 times the spin resistance of the bad metal, then I can start injecting spin efficiently. This idea was put forward by Fert and Jaffres in 2001 and suggests that if you insert a tunnel barrier between the metallic polarizer and the semiconductor, then you can efficiently inject a spin current. We'll conclude this discussion with two experimental achievements realized about 10 years ago and that demonstrate efficient spin injection in silicon using transition metal spin polarizers. The first experiment is due to Applebaum and coworkers. To circumvent the resistance mismatch issue, they injected hot electrons from the metal into the silicon channel. That's a very challenging experiment, as it requires applying large voltages across the heterostructure. The second experiment is due to Dash and coworkers. The authors used a lateral spin valve, and they insert a tunnel barrier between the polarizer and the silicon. This allows them to inject spins on the one side and detect them on the other side. This way, the authors could evaluate spin relaxation length up to 300 nanometers at room temperature. We have seen how spin accumulates at interfaces and how ferromagnets can be used to create spin-polarized currents. Now let's consider a device made of two ferromagnets separated by a non-magnetic metal. This is called the spin valve. On the left diagram, I represent the typical spin accumulation profile when the magnetizations of the two ferromagnets are parallel with each other. On the right diagram, I represent the spin accumulation profile when the magnetizations are anti-parallel to each other. You see that in the latter case, there's a large spin accumulation in the central layer, which must be accompanied by a corresponding increase in the overall resistance. I can see that by computing the chemical potential profile in the parallel and anti-parallel configurations. As I just mentioned, the chemical potential accumulated across this device is larger in the anti-parallel configuration than in the parallel configuration. This results in a change of overall resistance, which is called the magnetoresistance. Concretely, I obtain this formula. You can see that this formula involves the spin resistances of the three metals composing the device. Here, d is the thickness of the central layer, and lambda SF is the spin diffusion length. In the limit where the spin diffusion length is much larger than the spacer thickness, we obtain a magnetoresistance that is proportional to the spin resistivities in series times the polarization of the left and right ferromagnets. And the signal is then completely independent on the thickness of the spacer as long as it is smaller than the spin diffusion length. On the opposite, if the spin diffusion length is shorter than the spacer thickness, the magnetoresistance decreases exponentially with the thickness of the spacer and is proportional to the spin resistivity of the spacer. This device was originally introduced by Bernardiani and his colleagues at IBM. Here I give the original magnetoresistance measured at room temperature in nickel iron, copper nickel iron. The top figure shows the overall magnetization of the device as a function of the magnetic field, while the bottom panel gives the corresponding magnetoresistance curve. One of the nickel iron layers is spun by iron manganese antiferromagnet through exchange bias, so it has a larger coercivity than the other nickel iron layer. Therefore, by starting from large negative magnetic field, the magnetizations of both nickel iron layers are parallel to each other, pointing downwards. Then, by decreasing the field magnitude and changing its sign, the layer with the lowest coercivity switches first. Finally, by further increasing the magnetic field, the layer with the largest coercivity switches, and we obtain a parallel configuration, both magnetizations pointing upward. The bottom diagram shows the corresponding resistance of the slab, and you see that when the magnetizations are parallel to each other, you get a low resistance, and when they are anti-parallel to each other, you get a high resistance. Technologically, we are interested in this loop, which is called the minor loop. In this region, one can reversibly switch between high and low resistance states using reasonably small magnetic fields. Therefore, you can use this spin valve as a sensor or as a magnetic memory device. Notice that the magnetoresistance remains rather low, just a few percent. Device engineering can boost it up to about 10%, but not much more than that. Let us look at how materials parameters influence the magnetoresistance. If you increase the thickness of the spacer, you shall observe a regular decrease of the magnetoresistive signal, as observed here. Now it's important to mention that this decrease is not solely attributed to the spin relaxation taking place in the spacer. It is also due to the fact that adding more spacer material enhances the overall resistance. Therefore, when we look at the ratio between the magnetoresistance and the resistance of the full device in the parallel configuration, we end up with an additional algebraic decay. Similarly, if you increase the thickness of the ferromagnet, you first see an increase of the signal because you improve the spin polarization of the flowing current. But after a while, adding more ferromagnetic material does not increase the spin polarization anymore, and on the contrary, enhances the overall resistance. Therefore, you end up with a steady algebraic decay at large ferromagnetic thicknesses. So this tells you that in metallic spin valves, you have to be very careful not to add too resistive materials. Otherwise, you simply quench the signal. Hence, you need to smartly engineer the device and choose the proper materials combination to optimize the spin polarization. In the decades that followed the discovery of the giant magnetoresistance, a lot of experimental studies have been conducted to determine the materials parameters of a wide variety of metallic thin films, and in particular their bulk polarization and spin diffusion length. In this table, I give you a few examples of typical materials used in spin valves. Let's take the first three transition metal ferromagnets: cobalt, permalloy, and cobalt iron. They possess moderate resistivity and can display quite strong polarization, 60% for cobalt iron and 70% in the case of permalloy. Their spin diffusion length at room temperature is between 5 nanometers for permalloy and 25 nanometers for cobalt. So permalloy and cobalt iron are actually pretty popular spin polarizers due to their strong polarization and fairly short spin diffusion length. Copper is a very useful spin transmitter and often serves as a spacer or as a channel to transmit spin. Indeed, its resistivity is quite low, and most importantly, it possesses a long spin diffusion length of about 100 nanometers at room temperature. This fairly large spin diffusion length comes from the fact that the D shell of copper is filled, and therefore the influence of spin-orbit coupling is quenched, resulting in a weak spin relaxation. On the contrary, platinum has a moderate resistivity, and due to its strong spin-orbit coupling, it possesses a short spin diffusion length, between 3 to 10 nanometers maximum. So although it is not very pertinent to use it as a spin channel, its strong spin-orbit coupling makes it an ideal source of pure spin currents. This is something we'll see in the last lecture. Finally, the last material I'm showing here is an antiferromagnet, very useful in spin valves to pin proximate ferromagnets via exchange bias. However, its resistivity is quite high, and its spin diffusion length is very short, so it tends to substantially reduce the magnetoresistance ratio in metallic spin valves. Another series of parameters that needs to be determined experimentally concern the interfacial properties. In the previous discussion, I mentioned the importance of interfacial resistance and interfacial polarization. I should also mention that scattering at interfaces can in principle induce spin flip. As a matter of fact, interfaces can enhance momentum scattering and therefore spin relaxation. In other words, the spin current is never perfectly transmitted, and there's always spin memory loss. It is often modeled by introducing an effective interfacial layer with an artificial spin diffusion length. What characterizes this interfacial spin flip is the ratio between the thickness of this interfacial layer and the effective spin diffusion length. In this table, I give some of the numbers obtained in the literature. Cobalt copper and permalloy copper are two of the most popular interfaces in Spintronics devices. They pretty much look alike, although cobalt copper shows a larger interfacial resistance. Notice that they both display interfacial polarization that is a bit larger than the bulk polarization of cobalt or permalloy. Finally, they both possess decent spin memory loss, about 0.25. Cobalt ruthenium is an interesting interface because it is often used to create synthetic antiferromagnets. Remarkably, the interfacial polarization is negative. So this kind of interface tends to depolarize incoming spin currents. I also give here cobalt platinum and copper platinum, which both show very strong spin memory loss due to the strong spin-orbit coupling of platinum. You can find much more information about the methodology to extract these parameters, as well as a critical discussion of the values extracted from the experiments in this extensive review by Jack Bass.
We have seen many important things in this lecture. First, I emphasized the role of spin diffusion, which enables the build-up or the loss of the spin polarization of a charge current. We have also seen that when electrons flow through an interface, spin density accumulates, leading to spin accumulation giving rise to interfacial resistance. Spin accumulation and spin current are the most important concepts of spintronics. Using these concepts, one can build up a magnetic spin valve that displays magnetoresistance. The magnetic spin valve is the cornerstone of applied spintronics. Up till now, we have only talked about transport in metals. And as a matter of fact, the magnetic spin valve is composed of two metallic ferromagnets separated by a metallic spacer with a long spin diffusion length, like copper or aluminum. Now, what happens if I replace this metallic spacer by a tunnel barrier, like aluminum oxide or magnesium oxide? To learn about that, let's jump to the last part of this lecture.